So if we can sketch the problems, yeah, so the problem should look like this, where we have three different surfaces of sphere. Okay, so we have three spheres, right? So that should be spheres of 1 centimeter radius, okay, 1 cm. Then we have a sphere of 2 cm, okay, and then we have the third sphere of 3 cm. Sorry, yeah, it's not nice, the drawing for my spheres, sorry for that. Okay, so we have three spheres with different radius, and each of them are said to carry different charge distribution, which are 20, -9, and 2 nanocoulomb per meter squared. So looking at this unit, it is understood that the charges are said to be a surface charge type. Yes, surface charge type. So if we can label it, we're going to have, this is 2 nanocoulomb per meter squared. So that should be -9 nanocoulomb per meter squared. And the inner part will be a 20 nanocoulomb per meter squared. Yeah. So it is said that the charge is only located on the surface, yeah, on the surface of the sphere, no charge elsewhere. So you have to understood the behavior, the placement, the location of the charges. Yeah, it is only located on the sphere surfaces. Okay, so you have to understand that. Okay, so the question now is, number one, how much electric flux leaves the spherical surface of 5 centimeter? Okay, so 5 cm by right should be somewhere outside this sphere. So let us draw a sphere, okay, a sphere, and which I draw it in a dotted lines, yeah, which is imaginary. Okay, so the sphere is having a radius of 5 centimeter. So the question is, find the flux that leave this particular charge of this sphere of 5 centimeter. Okay, so as what we have learned, the basics of Gauss law states that the flux leaving the sphere shall be equal to the charge enclosed. Yeah, yeah, the flux leaving the closed surface. Yeah, the flux leaving the closed surface is equal to the charge enclosed inside the closed surface. So if you want to find the flux leave the surface, what you have to do is that you have to find the charge that is said to be contained inside the closed surface or spherical surface in this case. Yeah. Okay, so based on this, we know that our closed surface is a 5 cm in which all the spheres that we are given, yeah, basically are located inside the 5 centimeter surface. So the Q enclosed by right, or the flux leaving the surface by right can be calculated by simply find out the charge enclosed inside the surface, which will be rho SDS for surface number 1 plus rho SDS for a surface number 2 and rho SDS for a surface number 3. Yeah, so we have three surfaces there. Okay, in which if we can say that number 1 is for 1 centimeter sphere, 2 is for 2 centimeter sphere, and 3 is for 3 centimeter spheres. So for this, we can straight away find the charge amount in which you're going to have, for the inner should be 20 nanocoulomb, so 20 nano multiplied with 4 pi, r should be 1 cm, so it should be 0.01 squared. Okay, that should be the charge amount for 1 centimeter sphere radius, plus for the second sphere, which is -9, yeah, and the area will be 4 pi of 0.02 squared, plus the third one should be 2 nano, yeah, 2 nano, 4 pi, radius will be 0.03 squared. Okay, so that should be the amount of charge that is said to be contained inside the 5 centimeter sphere. So that charge amount shall be equal to the flux leaving the 5 centimeter sphere. Yeah, so that should be the answer for part A of these questions. Okay, so this is the basis of Gauss law. The flux leaving the surface is equal to the charge inside the surface. Yeah, right. Hopefully you are clear regarding these issues. Any question for this? No? Okay, so I proceed with the part B of the questions. So part B basically is to find the flux density D, yeah, at this position, which is in Cartesian, where we have 1 cm, -1 cm, and 2 cm position, location. So if I can sketch this P point accordingly, Okay, so that should be x axis, that should be y axis. Okay, and that should be z axis. So this point of P by right should be located somewhere here. Yeah, this is 2. So we're going to have point here. Okay, that should be position of 1, -1, and 2 cm. Yeah. So if we base on the sphere system, we can see that the radius should be equal to this length. Yeah, from the origin to point of 1, -1, 2, in which the radius will be equals to set of 1 squared plus 1 squared plus 2 squared, which will give us set of 6. So basically, the point of P here is having a radius of set of 6. Yeah, a radius or a set of 6, which is a radius for a sphere. Yeah, a radius for a sphere, which is said to, the surface of this sphere is said to having a point of 1 cm, -1 cm, and 2 cm. Okay, so basically, we need to find the d. Yeah, we need to find the d at this position, the point of P. Okay, so we need to identify where is the location of this P. Is it less than 1? Is it between 1 and 2? Is it between 2 and 3 centimeter radius? Or is it bigger than 3 centimeter radius? So based on this, since the value of r equals to set of 6, so this position of a point of P should be located somewhere between 2 cm and 3 cm sphere. Yeah, that should be location of this point of P. Okay, so our interest is to find the flux density d at this position. That should be our aim now, yeah, because we want to find the d basically at this point of P. So before we can find the flux density d at the point of P, we need to first obtain the general value or general equation for the flux density d at this position. Yeah, because this is the position where the point P is said to be located. Okay, so for this, let us proceed with the Gauss law. Okay, so let us sketch the sphere first. Right, so that should be our 1 cm, that should be our 2 cm, and that should be our 3 cm sphere. Okay, so our interest is between 2 and 3, yeah, because this is the position of interest. So let us sketch the Gaussian surface. So as we have learned before, the Gaussian surface to be used here will be a sphere. Yeah, sorry for this. Okay, so that should be our Gaussian surface to be used between 2 and 3 centimeter, right? So from the Gauss law, which state that d dot ds equals to enclosed charge. So the left-hand side will be the integration on the Gaussian surface, and the enclosed charge is the charge inside the Gaussian. So this is what we have done before. Right, so I think we can proceed with the Gauss law now. Left-hand side will give us dr. Okay, so as what we have learned before, we only choose one direction for the flux density d. Yeah, so knowing that for the spherical, you're going to have r theta and phi for the direction of d, for the d vector, and we only choose one, which is the radius direction. The reason for this is because we can assume that the sphere is originated from a point charge. Yeah, a point charge. So a point charge is knowing to have a direction of d or e in the direction of r. So due to that, we can say that the sphere or the spherical surface will also having the direction of d, which is r direction. Yeah, so we're going to have d as a dr of r, and ds will be equals to r squared sine theta d theta, sorry, r squared sine theta d theta d phi, direction of r, that should be the ds. And the enclosed charge, if we base on this, we are going to have two spherical surfaces which are said to be enclosed inside the Gaussian, which are the sphere of 1 cm and the sphere of 2 cm. Yeah, the sphere of 3 cm can be ignored because it is located outside the Gaussian. Yeah, so we can ignore the third surface. We just consider the enclosed sphere, which are 1 cm and 2 cm sphere. Okay, so we're going to have the enclosed charge can be now written to be rho s ds, surface sphere number 1 plus rho s ds for sphere number 2. Yeah, that should be the case. Yeah, sphere number 2. Okay, we proceed now. That should be going to have dr 4 pi r squared for left hand side For the right hand side, that should give us 20 nano, yeah, 20 nano, and 4 pi r squared, yeah, which is 1 squared or 0.01 squared, okay, plus for the second surface, which will be negative 9 nano, and the area will be 4 pi 0.02 squared. Okay, I forgot to mention to you just now that this will be our area. R is a variable, yeah. R is a variable which is in which R can be any value between 2 and 3 centimeter, yeah. Yeah, R is a variable which is the radius of your Gaussian surface. Yeah, R is the radius of the Gaussian surface, and the value of R can be between 2 and 3 centimeters. Yeah, so that's why this R here is related to this R. Yeah, it's the same things. Okay, so we can proceed further. So I need to erase this part. Okay then. So we're going to have a dr. Okay, 20 nano, or 4 pi can be cancelled out straight away. So 20 nano with 0.01 squared minus 9 nano 0.02 squared divided by r squared. Okay, so knowing that the vector d equals to dr direction of r, so we're going to have the value vector of d should be based on this value, yeah, which will be 20 nano 0.01 squared minus 9 nano 0.02 squared divided by r squared direction of r. Yeah, coulombs per meter squared. Okay, so what we have obtained here finally is the flux density d for a value of r, for radius of r, in which this radius of r is only within 2 centimeter and 3 centimeters. Yeah, right? So this is the flux density within 2 and 3 centimeter radius. So as such, we can obtain the flux density d at the point P, which is requested on the question, in which the flux density d at point P can be obtained by simply substituting the value of r to be equal to set of 6. So, yeah, so at P, when r is equal to 6, so we can find what should be the value of vector d. So that should be our vector d in coulombs per meter squared. Okay, so simply we can find the flux density d by substituting the value of r equals to of 6 in our obtained terms of d previously. Yeah, so that should be the flux density d at the requested point of P. Any question for this? No? So I proceed with the second part of the question. Next question will be example 6. Okay, so again, we are given a spherical surfaces, spherical problem still. This time we are having the position of the radius at 2, 4, and 6 meters. Each of them having this density of charge in nanocoulomb per meter squared, which means that these three are surface charge densities. Yeah. So let us sketch it to be. Okay, we sketch it. It's going to have, this is 2. Okay, that should be 4. Okay, and that should be 6 meters. Yeah, so that should be location. I mean the position, the sketch of your problems. So each of them are having different charge distribution: 20 nanocoulomb per meter squared, negative 4 nanocoulomb per meter squared, and we have a unknown value just given. We are just given the value of rho s naught. Okay, first of all, I mean, based on this given information, find the flux density d at these three positions, which is at 1, 3, and 5 meters. Okay, we'll go for the first one, which is at 1 meter. So r equals to 1 meter. So 1 meter is located inside the 2 meter radius, yeah, which is inside the inner sphere. Yeah. So this 1 meter is related to a position of r. R is a variable which is less than 1 meter. So this is our point of interest, our position of interest, yeah, which is less than 2 meters to be exact, yeah. Sorry. Less than 2 meters. Okay, so that should be our point of interest, r less than 2 meters, in which this r is a variable which can take any position inside this inner sphere. Yeah. So let us sketch using the Gauss law, I mean the Gaussian surface for this. Okay. that should be our Gaussian surface. Any position of r less than 2 meters, so I put r here to represent the Gaussian surface radius. Okay, so we can write the Gauss law, the d dot ds equals to enclosed charge. Sorry, my mistake again. Sorry for this, yeah. This is 2, this is 4, and this is 6. Okay, so for the first one, r equals to 1 meters. Our interest will be at this position, which is less than 2 meter region. Yeah, so we based on the Gauss law, the d dot ds equals to the enclosed charge. Yeah, so our interest will be a position here. Yeah, which is less than 1 meter. That's our r. Less than 2 meters. Sorry, less than 2 meters. Okay, so based on the Gauss law, we have this d dot ds equals to q enclosed. This will be the integration on the Gaussian surface. The enclosed charge is the charge inside the Gaussian, inside the red sphere. Okay, so based on this, we can further write that left-hand side will give us dr 4 pi r squared, but the enclosed charge is, which is charge inside the Gaussian, so that should be equal to 0. Yeah, because why? Because based on the questions given, your charges are only located on the surface, yeah? On this particular surface, on this surface, and on the surface of spheres. So no charge elsewhere. So due to that, for the first case, the enclosed charge inside the Gaussian shall be 0. And from this, we can write that the vector d shall be equal to 0. So any point within the 2 meter sphere radius, that flux density d will be equals to 0. Okay, so any point within 2 meter radius sphere, the flux density d value shall be equals to 0. Yeah. Okay, so we go for the second one, which is for the 3 meter position. So r equals to 3 meter, by right, is located within 2 and 4. Within 2 and 4, yeah? So our region of interest is r between 2 meters and less than 4 meters, yeah? That should be our region of interest. So we need to sketch the Gaussian surface for this region, yeah, which is here, between 2 and 4 meters. Okay, so that should be our R now. Yeah, our R now, which is we considered for this particular region. Okay, so based on the Gauss law, the d dot ds equals to the enclosed charge. Okay, so as what we have learned before, the left-hand side is the integration on the Gaussian surface. The right-hand side is the integration inside the Gaussian. Yeah, so we proceed further. We're going to have for left-hand side will be dr 4 pi r squared, and the enclosed charge, which is charge inside the Gaussian, is only consists of a single sphere of 2 meter radius, right? Yeah, only 2 meter radius. So the enclosed charge can be simply written to be integration of rho s ds, and further on we're going to have dr 4 pi r squared, and rho s will be 20 nano 4 pi r squared, which is 2 squared. This is the charge amount for the 2 meter sphere. Yeah, 2 meter sphere. So we can cancel the 4 pi, and going to have dr shall be equals to 80 nano over r squared. And further on, we can see that the vector d will be dr direction of r, which will be 80 nano over r squared, direction of r, coulombs per meter squared. Okay, so this is the general terms of vector d for any value of r which must fulfill this position between 2 and 4. Okay, so due to that, at r equals to 3 meters, to find the flux density d at this point of 3 meters radius, we can simply substitute r equals to 3 in the equation here. So that will give us 80 nano over 3 squared, direction of r, coulombs per meter squared. Yeah. So that should be our flux density d at the position of r equals to 3 meter radius. Okay, so any question for this? No? Okay, so I hope that you can understand these issues clearly. Okay, I won't proceed with the 5 meter, so you can proceed on your own. The idea is the same. So for 5 meter position, which is between 4 and 6, the same applied method should be used, but have to be very careful on the enclosed charge now. Yeah, because for the region between 4 and 6, the enclosed charge will be two spheres enclosed inside the Gaussian, which are the 2 meter radius and the 4 meter radius. Yeah, the rest method are the same. Okay, right. So I will proceed with the part of the question, which is to determine the rho S naught. Yeah. So I'm going to erase all of these writing. Okay, so for the second part of the question, we are given a spherical surface. Okay, sorry for this. All right. So this is 2, this is 4, and this is 6, yeah? So our interest is at 7 meter radius, which is outside here. So let us sketch a 7 meter radius. Okay, sorry, 7 meter, R equals 7 meter should be located outside. So let us, okay, 7 meter radius is for the position of R bigger than 6 meters. Okay, so need to understand that clearly, yeah? Bigger than 6 meters. Okay, so we have 20 nano for 2 meter radius, -4 nano for 4 meter radius, and rho S naught for the 6 meter radius. Yeah. Okay, so for R equal to 7 meters, which is for a region of R bigger than 6 meters, so we need to sketch the Gaussian surface now. The Gaussian surface should be located outside here because our interest will be any point bigger than 6 meters. So that should be our R to represent this region of bigger than 6 meters. Okay, so we are going to have Gauss law, the d dot ds equals to enclosed charge. The d dot ds is the integration on the Gaussian surface. Enclosed charge is a charge inside the Gaussian. So we can proceed with the calculation. We're going to have dr 4 pi r squared. You can proceed on your own, yeah, on this method of calculation. So the Q enclosed will be having 3 different spheres enclosed, 2, 4, and 6. All of them will be included in the enclosed charge, yeah? Because all of these 3 are inside the Gaussian. So we are supposed to have rho S ds for 2 meter, rho S ds for the 4 meter, plus the rho S ds for the 6 meter radius. Okay, so have to include all of them. So we proceed with that right hand side. So that will give us 20 nano or 4 pi 0.0, so 0.2, sorry. My mistake then. Okay, sorry for that. 4 pi 2 squared, okay, plus or minus 9 nano 4 pi times 4 squared, okay, and plus rho S naught. Okay, rho S naught times 4 pi of 6 squared. Okay, that should be give us dr. Okay, that should give us dr 4 pi r squared. So 4 pi can be cancelled out for all the terms here. So end up we're going to have dr shall be equals to 80 nano minus 16 times 9 nano. Okay, plus 36 of rho S naught. Okay, divided by r squared. Yeah, r squared. Okay, and from here we can find the flux density D in general, yeah, which is in dr of r terms. Okay, so basically the vector D that we obtain from these dr terms is only valid for the value of r here, value of r, in which this value of r must only for r bigger than 6 as stated here. Yeah, r bigger than 6. Okay, so it means that r equal to 7 can be substituted in this equation because r equal to 7 meter is outside 6 meter radius. So due to this, given this condition that d equal to 0 at 7 meter radius, we can say that when d equal to 0 at 7 meter radius, that will give us 0 equals to 80 nano minus 16 times 9 will be 144. Yeah, 144 nano minus 36 of rho S naught divided by R squared. Okay, so sorry, R will be 7 meters, sorry, 7 meter now, yeah, 7 meter, 7 squared, yeah. Okay, so from this equation, we can obtain the rho S naught, yeah, because rho S naught is the only variable in this equation, so that will give us the rho S naught value, yeah. So based on the conditions here, we can find the rho S naught. Okay. Right. Any question for this example?
Doctor, may I know why is negative 36?
Negative 36. Let me see. I think I made a mistake now. Sorry for that. It should be positive. Thank you, Wilhan. Okay.
Thank you.
Thank you. Okay then. Hopefully you are clear getting the Gauss law, yeah?
Sorry, doctor.
Yes.
I think I can't see your screen. I cannot see your screen. It's like a blank.
How about the
Is it
others? Can you
only me?
see? How about the others? Can you see my screen clearly?
Yes, we can see.
Yeah, I think you have a problem with the connection. Yeah?
Okay.
Ihsan, yeah?
Try to
Is it Ihsan or Fadilah, yeah?
Fadila.
Fadilah, I think you need to exit and then come in. I mean, enter again. Is it okay?
Okay.
Okay. Right. All right. I want to proceed with the example 5. I'm going to proceed with the. You can do it on your own, yeah. For all the examples given here, the one that I didn't, that I do not proceed in the class, you can do on your own. Try on your own. So if you want to ask the questions to confirm your answer, please PM me, or you can discuss with me later on, yeah? Okay, I will proceed with this example 6 also. My concern will be on a sample test 1 here. Okay, for this sample test 1, the problems is similar to what we have done earlier in the example. So I will proceed with this. You can proceed on your own. Try to answer this sample of test 1 on your own. Again, any questions you can ask me later, yeah? My concern will be on this sample test 1, this question. Okay, these questions, we are given a non-uniform volume charge density, rho v, which is of 120 R coulombs per meter cube. Okay, we are given a volume charge structure, lies within a spherical surface of 1 meter and rho v equals to 0 elsewhere. Okay, so if I can sketch the problems, it should look like this, where we have a sphere. Okay, the sphere is having a radius of 1 meter. Okay, and the density for this will be rho v. So means that charge is inside the sphere. Rho v is 120 R. Okay, 120 R coulombs per meter cube. Okay, which means that we are dealing with the volume charge density. Yeah, as for the previous examples that we did just now, we are dealing only with the spherical surface. I mean, the surface charge, yeah? The surface charge. But for these examples, the problem is related to the volume charge. Okay, so the volume charge, the charges are said to be inside the sphere. The surface charge, the charge are said to be located only on the surface of the sphere. So need to distinguish between these two charge distributions clearly, yeah? Okay, so that should be the sketch of your problems. Okay, so our concern will be on the first questions here. Using Gauss law, find the electric flux density everywhere. So we have two position or two regions in general. The first region is R less than 1 meter. Okay, the second region is R bigger than 1 meter. Yeah, so we have two regions there. 1 meter, less than 1 meter, and bigger than 1 meter. So we have to find the D for these two positions now. Yeah. Okay, let us proceed with the first region, which is less than 1 meter. So use the Gauss law. The D dot ds equals to enclosed charge. Okay, so for this particular case, we need to sketch the Gaussian surface as usual. So which is to for the region of 1 meter, less than 1 meter radius. So that should be our region of interest in the red colored surface or red sphere. That should be our area. R is for the region less than 1 meter. Okay, then we can have this equation, Gauss law. This will be on the integration on this particular Gaussian surface. Enclosed charge is a charge inside the Gaussian as usual. We can proceed. We're going to have dr 4 pi r squared, which is the integration for the left hand side, while for the right hand side that will give us integrations of 120 r squared sine theta dr d theta d phi. Okay. All right, so we can proceed now with the integration, right? So we're going to have dr 4 pi r squared. Right hand side, we're going to have 120 integration of r power of 3 dr, integration of sine theta d theta, d phi integration. Yeah, what should be the range of r now? What should be the range of r now? Can I ask Taufan Surya Putra, are you in the class now? No, yeah. How about Felix Erickson? Also no. How about Hong Jingxiang? Are you in the class now?
Yes, doctor.
Okay, Jingxiang, thank you. What should be the range of R for these particular problems?
0 to 1.
0 to, so 0 correct, but the endpoint should be at which position?
R.
Thank you very much. Yeah, because the enclosed charge is only between 0 and R. Yeah, so you have to put the range of integration from 0 to R. Okay, thank you, Jingxiang, for your answer. Very good. And hopefully all of you can understand, yeah, why not 1? It should be from 0 to R. Because you have to calculate the charge enclosed inside the Gaussian. So as what I've drawn here, your Gaussian surface is only bounded from 0 to R. So you have to put the integration from 0 to R, yeah? So have it very clear on this. Thank you for your answer. Okay, theta is known to be 0 to pi, and phi from 0 to 2 pi, because your Gaussian is a full sphere. So theta and phi should be no problems. It will go to maximum for both of them. Okay, we can proceed now for the rest of these calculation. Okay, I don't have much surface. I'm going to use the top surface here. Okay, so from the bottom, I mean from this part, we're going to have dr, yeah, 4 pi r squared, and the right hand side will give us 120 4 pi, yeah, I proceed with the sine theta and d phi integration. 4 pi should be there, and for the r integration, that should give us r power of 4 divided by 4, yeah. Okay, so 4 pi can be cancelled out, r squared also can be cancelled out with this. We're going to have 2 only now, so your dr will be 30 r squared, yeah, 4 and this will be 30, so it will be 30 r squared, in which that we're going to have d vector as dr of r, which will be, sorry, so that will give us 30 r squared, the ration of r coulombs per meter squared. Okay, so that should be our flux density D for any value of r in which r must be less than 1 meter. Yeah, so this is variable. Remember, this r is a variable that you get here. R is only valid for region of r less than 1 meter. Okay, we now proceed with the second region, which is bigger than 1 meter now. Okay, so as usual, we write the Gauss Law Equation, D dot ds equals to the enclosed charge. Okay, so now we can sketch the Gaussian surface for the second region. So bigger than 1 meter, that should be our Gaussian surface, which is outside the 1 meter sphere, and we put r as a variable now, yeah? So similar to the previous, but now the sphere is bigger, is larger in terms of the radius, and I'm sorry, Fadila, I'm not sure what's the problem. Yeah, I'm not sure what's the problem. I'm sorry for this, yeah, because your friends don't have this kind of problems. Yeah, Fadila, I'm very sorry for this. Yeah, nothing can be done at my side. Yeah, I have to proceed there. Thank you. Okay, so then we're going to have a dr 4 pi r squared for the right hand side, so left hand side, sorry. And the enclosed charge will be the charge inside the Gaussian. Yeah, so that should be the enclosed charge, which is the charge inside the Gaussian. This will be the integration on the Gaussian surface, okay. Right, so the enclosed charge is only charged within this sphere only, yeah, no charge elsewhere. It means that from this diagram, we only have a charge from 0 to 1 meter, no charge elsewhere. So your enclosed charge will be solely from, yeah, solely from this charge of 1 meter radius. So for that, we can write the integration of Q enclosed to be integration of 120 r r squared sine theta d theta d, sorry, d r d theta d phi. Okay, so we can proceed with dr 4 pi r squared 120 integration of r power of 3 dr integration of sine theta, sorry, sine theta d theta integrations of d phi. Okay, so for this particular region, range of integration of r will be from 0 to 1, yeah, 0 to 1, because that should be the position where we have the charge. Yeah, we cannot integrate from 0 to r, yeah, not 0 to r, because from 1 to r there is no charge, so it's useless to integrate between 1 to r. Yeah, so that's why we have to put the range from 0 to 1 only. Okay, theta 0 to pi and phi from 0 to 2 pi, yeah. Okay then. Right, so I proceed with the here. So we have dr 4 pi r squared, and have 120. So that will give us 1 over 4, yeah, for the r integration. And we're going to have 4 pi here. Okay, and 4 pi can be cancelled out. So we're going to have dr shall be equals to 30 divided by r squared. Yeah, and from here we're going to have vector d shall be 30 over r squared, direction of r, coulombs per meter squared. Okay, so that should be our vector d for a region of r bigger than 1 meter. So you can see the difference between the two, yeah. So this is for r less than 1, and this is for r bigger than 1. Okay, so that should be the difference between the two. Okay, any question for this example? Okay, sorry Fadilah, yeah, I cannot do anything. Yeah, the worst that we can do is I have to, the video is recorded. Yeah, so hopefully you can have a revision based on the recorded videos. Yeah, I'm very sorry, we cannot do anything on this. Okay. Okay, hopefully you are clear regarding these problems. Yeah, okay, I go proceed with part B of the questions. Any more question on this? No, yeah? Okay. Okay, part B of the question, we are given a, okay, now it's stated that for part B, the surface charge density is given with a density of rho S2, which is unknown. And this rho S2 is located at a surface of 2 meters. Yeah, so it's given that that if in that density, or the d, yeah, this is d, yeah, at r equals to 4 meter is equal to 0. Okay, assuming the center for both spherical structures are at the origin. So it means that both spheres are said to be having same center, yeah. Okay, so now if I can sketch the problems to make it clearer for all of you, we are having this volume charge, which is 1 meter, initially given the questions. Yeah, this is rho v, yeah. So I can put this is a rho v charge. So it's given now at 2 meter radius. Okay, this is 2 meter. Okay, it's 2 meter now. So I label this as 2 meter. Okay, there is a new charge density located on the surface, rho S2, because it's given to be a surface charge density, yeah. The surface charge density means that the charge is only located on the surface. Okay, it's different with this rho v. Rho v is charges everywhere inside the sphere, yeah. Okay, so we need to, is given that the electric field density at r equals to 4 is equals to 0. Okay, means that you need to find the flux density d for a region of r bigger than 2 meter. You need to find the flux density d for this region. So that is our aim now, because 4 meters is outside or bigger than 2 meters, yeah? So you need to find the flux density first, and afterwards you need to equate the flux density D to be 0 at 4 meter value. Okay, so that is the trick, the tips behind these problems, yeah? Okay, so let us proceed with the solution. So as usual, we proceed the Gauss law, d dot ds equals to enclosed charge. Okay, so need to sketch the Gaussian surface first. Yeah, Gaussian surface, which is for r bigger than 2 meter. So your Gaussian should be located here, yeah. Okay, so that's about Gaussian. Okay, that's about Gaussian surface. So that should be area, given to be r, which is to represent this area, r bigger than 2 meters. That's why we have r here. Okay, so this will be integration on the left-hand side, will be on the surface integration. Enclosed charge is the charge inside the Gaussian, yeah? Okay, so now we can proceed for left-hand side integration. That will give us dr of 4 pi r squared. Okay, 4 pi r squared for left-hand side. And for the right-hand side, with the charge inside the Gaussian, we have two charges now, which are the volume charge and also the surface charge, yeah? So we can write this as, so you're going to have 120r or 120 integrations of r power of 3 dr, integration of sine theta d theta, integration of d phi. So similar to what we have done before. So you can do it on your own, yeah? Okay, due to 2 pi plus due to surface charge now, which is rho s2 multiplied with 4 pi r squared, yeah, which is at 2 meter. Okay, so that should be your charge enclosure. Consists of two charges, which are the volume charge given on the first term, and the surface charge, which is given in the second term. Yeah? So that should be the enclosed charge by the Gaussian. Right, so we can proceed with the integration. We're going to have dr 4 pi r squared, and that will give us, 4 pi, that should be 30, yeah, and 4 pi should be there, divided by 4, divided by 4, okay, sorry, what's 120, 120, right, and plus rho s2 with a 16 pi here, okay. Right, so we can simplify the equation. 30, 4 pi can be cancelled out. With this, going to have 4 only. I bring it up here. So we're going to have dr equals to 30 plus 4 rho s2 divided by r squared. And subsequently, we can write the vector d equals to dr direction of r, which will give us 30 plus 4 rho s2 divided by r squared direction of r, yeah? So that should be our vector d, which is equivalent, the vector d that we obtain here is valid for a value of r bigger than 2, yeah? Value of r bigger than 2. So due to that, we can say that at r equals to 4, okay, we can say that vector d will be equals to 30 plus 4 rho s2 divided by 4 squared, direction of r, okay, and it's given that at r equals to 4 meter, your flux density d will be equals to 0. So subsequently, from these terms that we obtain here, we can write that 4 rho s2 shall be equals to negative 30, yeah, negative 30, which will give us rho s2 as negative 7.5 coulombs per meter squared. So that should be our rho s2 value. Yeah. Right. Okay. So I need to put here that at r equals to 4, the vector d equals to 0. Yeah. Just to make clear for you. Okay then. Any question for this method of solution for part B of the question? No?
Doctor, For the R equal to 4, the
Mm-mm.
D is equal to 0, right?
Correct.
But in the question say electric field.
No, it's a density. Okay, electric field density, sorry, okay, electric field density, yeah, not intensity. Density, okay, this is D. The
Oh,
E
okay.
is electric field intensity, yeah?
Okay.
Okay, okay. We also call this as electric flux density, the same things, yeah? Electric flux density, electric field density are the same things, yeah? Okay. Any more question on this? No, yeah? Okay, if there's no question, I think we can proceed with parts of the questions here. So I need to erase all of these slides. Okay, part C is to sketch the dr versus r. Okay, so I think that should be no problem at all. That should be your r, that should be your dr. Yeah, when both distribution present. So basically, we have only two positions to be considered, which is from 0 to 1 and 2, I believe. Yeah. So this is 1, sorry, this is 1, this is 2. Okay, so for the first one, this is 30. Remember, yeah, so if I can rewrite this again for you, for r less than 1, we have the vector d as 30 r squared, the direction of r coulombs per meter squared. R bigger than 1, less than 2, the flux density d is equals to 30 over r squared, the direction of r coulombs per meter squared. And for r bigger than 2, we can see that the flux density d equals to 0. Okay, equal to 0, yeah, due to this argument just now, yeah. Okay, so from these three informations given for distinct regions, we can see that your sketch for the dr is the magnitude, yeah, magnitude of a vector d, so we just consider the magnitude of vector d here. So between 0 to 1, we're going to have a quadratic graph up to r equals to 1. Okay, sorry, r equals to 1, sorry for that, not straight line here. I have to erase this again. Sorry for this. Okay then, so that should be a straight line. Okay, so we are supposed to have a, yeah, okay, it should be like this, yeah, it should touch this 30, yeah, because at r equals to 1, the d magnitude will be 30, and then for r between 1 and 2, we're going to have 30 over r squared, so there's going to have this graph down here. Okay, and afterwards, sorry, 30 of r squared. Sorry for this. Okay, so let's say, okay, let's say this position here, this value here is 30 over 4. Okay, 30 over 4. So we're going to have a graph which will be reducing, okay, like this, right? Right, which is, okay, use a curve like this. And afterwards, for t, r bigger than 2, the d will be 0. So abruptly, it will move to 0 straight away like this. Okay, so that should be how your graph should look like. Okay. All right. Okay, any question for these solutions of part C? To sketch, we have sketched the magnitude of D based on the obtained flux density D for the previous A and B questions. Okay. Any problems? Any questions related to this?
Doctor, why are R bigger than 2, the flux density is equal to 0?
Okay, because if we base on the equation for the part B just now, we have obtained that for R bigger than 2, your flux density D is given by, sorry, let me recall back the equation just now, is equals to what then? Is equals to what? Can you please help me? Going to 30, right? 30 plus, sorry.
Plus 4 rho S2
Yeah.
over R squared.
Yeah, so 30 plus 4 rho S2 divided by R squared, right? Am I right then? Okay, good. So we have obtained that based on the given conditions, rho S2 is equals to negative 7.5. coulombs meter squared, right? So when we substitute this equation to this term, to this equation here, we are having that the flux density D for R bigger than 2 will be equals to 0 all the way for R bigger than 2. Am I right? Okay. All right. Hopefully it's clear, yeah, Rehan, yeah? Okay, good. Okay, is there any questions on these examples here? No, yeah? Okay, if there's no questions, I think I can proceed with the, okay, I won't be doing this sample test one. Okay, so please try this on your own, yeah? Try this on your own, yeah? So this is a pattern of test questions, yeah? We want to evaluate the student understanding on topics related to Gauss law that you have learned in class, yeah? Hopefully, you have a good understanding on Gauss law based on what we have learned so far, yeah? Okay, so that's the end of lecture 6. So I believe that we have covered the Gauss law successfully. Is there any questions for lecture 6? No? Okay, if there's no questions, I think we can proceed lecture 7, which will be topics of divergence and divergence theorem. So this topic won't be long. It's a very short lecture because we want to introduce you to the concept of divergence, which will be used later in the subsequent lectures in EMT, yeah? Okay. Right, so lecture 7. Okay, sorry. Lecture 7 will be a topics of divergence and divergence theorem. So motivation for this lecture 7 will be to, is for the students to understand the divergence concept and also the application of divergence theorem. Okay, so divergence basically is related to the Gauss law, yeah? This is very much related to the Gauss law, yeah? Okay, so what's meant by divergence? Okay, so we have to start again with the Gauss law. So the Gauss law states that the d dot ds closed surface integration is Q enclosed, yeah? In which if we say that this is the case, yeah? This is the case, right? Where we have the charge enclosed here, a charge enclosed, yeah? A charge enclosed, and we are having a closed surface or imaginary surface, yeah? So it's given that the integration for the closed surface, here the surface will be a d dot ds integration. Okay, and the enclosed charge is given inside the Gaussian surface. Okay, so the concern now is what happened when this particular volume, yeah, this particular volume of your sphere is said to be shrink to 0. Yeah, it's said to be shrink to 0. So what will be the case if the volume of your Gaussian surface or Gaussian structure is shrink to 0? Okay, so this is the important things that need to be understood from the concept of divergence, yeah, because divergence basically is the flow of flux, from a point, yeah, flow of flux from a point, yeah, from a point. So due to this, we can see that when the closed surface volume are said to be shrink to 0, okay, we can then say that the volume of your Gaussian structure will be then approaching 0. Okay, so that should be the equations. Yeah, mathematically it should be given by this. Yeah, so we have, this is your Gauss law equation. Okay, the d dot ds, closed integration square enclosed. So what we did is that we divide this equation by delta V, whereby delta V is the volume of your closed surface. So let me recall it back. That should be our Gaussian surface. That is your enclosed charge just now. Okay, that is the charge. This is the closed surface integration. So delta V basically is this volume. Yeah, is this particular volume. All right. So we can see that when this equation of Gauss law, d dot ds closed surface integration equals to Q enclosed divided by delta V, and we put that delta V is, we put a limit to to the delta V, in which the limit is a delta V to be approaching 0, in which we are saying that these particular closed surface integration are said to be shrinking, yeah, are said to be reduced to a point. Yeah, the radius of your Gaussian surface are said to be reduced. Yeah, the R is said to be reduced, yeah, up to 0. Okay, so that's why we see that the left-hand side of this equation is equals to the divergence of D. So I mentioned just now, divergence is basically related to the flow of flux from a point. So that's why we see that the left-hand side here, yeah, left-hand side here is equivalent to the divergence of D. So this is basically a flux. Yeah, divergence of D is basically a flux. Yeah, a flux that is said to leave a point. Yeah, let's say we have a point. Yeah, if I can put that, if this is the case whereby the delta V is approaching 0, so we are going to have a single point here, a single point here, the charge enclosed. So that should be a flux leaving the point. Yeah, a flux leaving a point. So this flux that leave a point is noted to be a divergence of D, which is a flux amount, yeah, a flux amount. Okay, while the right-hand side is what we call as a volume charge, because we have the ratio of the charge divided by the volume. Yeah, so when the charge divided by the volume, that will give us a charge density. But this charge density is at a single point. Yeah, it's at a single point of x0, y0, and z0, or at this particular position, x0, y0, and z0. Okay, so basically we can have the equations of divergence of D equals to rho V, which is actually comes from where? It comes from a Gauss law, D dot ds equals to Q enclosed, in which you obtain this equation by putting that the volume of your Gaussian surface is approaching 0. Yeah, this equation of divergence is known to be a first law of Maxwell. Okay, so we have, I've mentioned this in our course information, the first lecture, last time, that we have the Maxwell's equation, yeah, which is the basic equation which are widely used, widely applied in electrical engineering. So we have 4 laws, yeah, 4 equations for the Maxwell's. So this is the first one. Yeah, this is the first one, which is basically originated from the Gauss law, which states that the flux must be originated from a charge. Okay, so that's the short description about the first law of Maxwell, yeah, which is related to the Gauss law, which states that the flux must always originated from a charge. Without charge, we cannot have a flux. Okay, so that is our understanding on the first law of Maxwell. Yeah. Right. So this is what I mentioned just now. Okay, I've explained to you these issues. Yeah, this is the case where we have a positive flux from a single point here. Yeah, a single point, a rho v charge positive. The flux will be pointing outward because the charge is positive. But when the charge is negative, we have the flux which is pointing inward, yeah, due to the negative charge that we have. Yeah, so basically this description for this phenomena is the same, yeah, where the flux must always originated from the charge. Yeah? Okay, then so the divergence basically is a vector quantity. Yeah, the divergence of D, yeah, divergence of D basically is a vector quantity in which it is based on the coordinate systems. So this is the equation for rectangular, equation for cylindrical, and equation for spherical. Okay, so please bear in mind, you don't have to memorize this, yeah? You don't have to memorize. All of these equations will be given, yeah? Don't have to memorize all of these divergence operations for different systems of coordinate, yeah? Okay, so I put here as a note, not to memorize, yeah? Not to be memorized. Okay, right. So this is about the example of related to the flux. Related to the divergence concept. basically we just base on the equations of divergence. For instance, yeah, if I base on the first equations here, find the volume charge density, yeah, find the volume charge density associated with each of the following field. Yeah, so I proceed with the first one, the D. We know that divergence of D is equals to rho V. So we can find the volume charge density rho V by simply evaluating the divergence of D. Yeah, for instance, if we have the D is xy squared, yx squared, and z in the rectangular system of coordinate, so we can see that the rho V will be equals to, dd over dx plus dd over dy plus dd over dz. Yeah, this is the dz, this is dy, and this will be dx. Yeah, yeah. So simply going to have what then? The dx over dx. So that will give us y squared plus x squared plus 1. So that should be our rho v obtained from the differentiation of the vector d with respect to different x, y, and z. Yeah. So that should be our rho v in the units of coulombs per meter cube. Yeah, because rho v is a volume charge density. Okay, so the same things applied for the part B of the question, yeah, which is to find the flux rho v charge for this given D. So knowing that this vector D is given in cylindrical coordinates, so you have to adopt these second equations down here, yeah, this one, to find the flux, to find the divergence of D. So you can try this on your own. So your answer obtained will be equals to rho v, a volume charge density. So you can try this on your own, yeah. Okay then, I think there's nothing much to be explained in this lecture 7. My concern is only on this divergence operation, yeah, in which we have successfully learned about the divergence of D equals to rho v, the first law of Maxwell, which actually comes from these equations of Gauss, d dot ds equals to q n enclosed, yeah. Okay. Right. So that this I won't be doing this example. You can try this on your own. Also, okay. The divergence theorem is a term which will be used later. I won't be covering these topics in general, in detail. But it is known that the divergence theorem is given by these equations here. Yeah, given by these equations here, which state that the d dot ds closed integration will be divergence of d dv, volume integration. Yeah. Okay, this is a divergence theorem which is applicable for any vectors. For any vectors. So this is a mathematical theorem. Okay, so this theorem will be used later in lecture 9 or lecture 10. Yeah, when you want to do some modification to the equation. Yeah, but I just introduced this theorem to you. Yeah, in which we can relate the surface integration with the volume integration. Yeah, so that's the purpose of divergence theorem. Yeah, so in other words, divergence theorem is a theorem which can be used to relate a closed surface integration with the volume integration. Okay, right. So detail will be learned later. Yeah, don't worry on this. Okay, so that's the end of chapter 3. So we have successfully covered chapter 3, starting from the flux and flux density concept. So these are the things that we have learned in the very beginning of chapter 3. And afterwards, we have learned about the relationship between the flux density and electric field. Okay, so if you can, this is a flux E and the D. This is a D and the E field relationship. Okay, and the third one is the Gauss law, d dot ds equals to enclosed charge. And we did few examples on the Gauss law, and you have to remember that the Gauss law is only applicable for a symmetrical case of charge distribution. Yeah, if facing a problems of asymmetrical charge, yeah, for example, finite length, finite area, so you have to go back to Coulomb's law. Okay, so this is what I have mentioned in class before. Okay, and finally, which is based on divergence, we have learned that the Gauss law that we have learned in lecture 6 has been modified or has been extensively used by Mr. Maxwell, yeah, in which he managed to obtain the first law of Maxwell, yeah, for a static field. Yeah, for a static field, we will have a divergence of D equals to rho V. So I just want to stress one more time that this equation of Maxwell and this Gauss law are identical, yeah, are same. Okay, so that's the end of chapter 3. We're going to meet again next week, in which we're going to start our lectures on chapter 4. Chapter 4 will be covering the topics of potential and also potential difference. Yeah, so